Okay, let's start. It's time to start. So please welcome Rob Elliott from ARM.
Yeah, thank you. Okay, thank you, Andrea. So my name is Rob Elliott. I'm the Director of Applied Machine Learning at ARM. What that means in practice is I look at our customers' use cases, our partners' use cases, how they decompose to run on our software stacks and our hardware, and try and find gaps in that and improve the system as a whole. And what I'm here to talk about today is a bit of a deeper dive into Arm NN. So hopefully all of you caught Jem's keynote earlier today where he spoke about what we're doing with Linaro, so this donation of engineering effort, this code base that we've been working on for a long time, and some of our aspirations with that. And so what I'm going to talk about is in more practical terms, what the Arm NN code base is, what interfaces there are and how people are using them, what Arm NN doesn't seek to do, so the problem space that we've carved out as we see as appropriate for inference engines, and then some ideas on areas for improvements and how you might get involved in working on the Arm NN code base and working with Arm and Linaro on this problem. So first off, this slide was also in Jem's deck, but I'll start to talk and decompose this into a bit more detail. So what is Arm NN? So fundamentally, it's a graph consumption API and inference API that is a runtime that runs on Android and Linux. On Android, it's integrated under Android NN and the NN API, and under Linux, it just runs directly connected. And so there's a couple of different ways you can interact with this. The first is connecting directly to the higher level frameworks. So we've got support for TensorFlow, Caffe, looking at support for PyTorch. In the latest release, we've got support for importing data from Onyx as well. The second way is integrating through an existing inference engine. So as you probably know, there are many different inference engines out there. We're integrating in another code base that we've released publicly with the Android NN API, so that's available on GitHub today. And then there are a number of other partner and customer inference engines that we've also integrated with as well. And then the other way you would typically interact with this is we have the starting point of a device interface. And that's really to open up and promote other people integrating their IP into the same stack. And the idea with all of this as a whole is that as you get data coming in from all of those different machine learning frameworks, we can get to this pinch point in the middle, which supports all of those, handles all of the tools and translations, quantization that you need to do to these networks to get them to run efficiently, and then helps you get that onto all of the bits of IP in the system. And we've done that by optimizing heavily for the CPU, GPU, and RMPU, and we're encouraging other people to get involved to do that for their IPs as well, or just to reuse this code base on their ARM CPU or GPU-enabled platforms. And so then to look at the Android side of this, so this breaks down in a number of different ways. So within Android NN API, there is a HAL, and that HAL is used for abstraction of many different devices already. Some of you may be aware. What we do with that is we have an implementation of our Arm inference engine. So that's the same code base that runs on Linux, and that allows you to access the GPU, or it allows you to access the MPU. So we'll run one instance for each of those. But we've also been doing a lot of work with Google over the past year or two, optimizing the CPU routines that are available in TensorFlow Lite and available in the Android NN API. And so on the Android deployment of this, you fall back to using the scheduler that is available within the Android NN API, and you're just using the Arm NN inference engine to translate those networks to run on the GPU or the MPU. And that's available open source today at the GitHub link there. And then moving on to talk about the deployment and the Linux, or indeed Android as well. So one of the things that we're finding is because Android releases are at a fairly low cadence, we're finding a lot of new operators that people are interested in as well. And so we try and run as fast as we can to keep up with all of the operators that people are interested in when they're processing these neural networks, be that new ways of doing convolution, new activation functions. And we expose that through this Arm NN SDK. And when you're running in this mode, the Arm NN SDK is acting as the runtime and the scheduler as well. And that can call through to the CPU, GPU, or RMPU, and then any other devices as well that you want to support in the system. And this is the path through which we support TensorFlow Lite, whereas with comparison on Android, that's handled by Google and the Android ecosystem instead. This is also available open source at the link here. So you can go and download that and try it out today. Our last release, which will in fact be the last release to this GitHub location, happened about 2 weeks ago. So you'll get the very latest code there. And with the Arm NN SDK, so that's the C++ 14 API for Linux and Android, and as I say, distributed on Arm NN. If you want to get a good overview of how the API works, go and look at that header file, or I'll also go through and talk through some of the details on what that interface is. So on that initial slide, I talked through a bit of on the framework integration options you have. So we've got support under Android NN and under Linux for TensorFlow. We've got support for Caffe as well, but we're starting to add support either for other frameworks directly, like MXNet, or via Onyx, which is looking to standardize the conversion from multiple different frameworks to run on various inference engines. And over time, our ambition here is to add support for more of these, but more importantly, I think particularly through the Linaro efforts, start to standardize on an intermediate form that can be used by Arm NN, can be used by other inference engines if they need to, can be used by tools that are optimizing these graphs, can be generated from a number of these different frameworks. And whether that's Onyx or some other intermediate form, I think remains to be seen. But getting to the point where you have compatibility from multiple different frameworks, answering really the fundamental question at the end of Chris's talk earlier was, how do we solve this deployment problem? This framework A runs on device A, framework B runs on device B, but framework B doesn't run on device A. How do you solve that problem? And that's really the heart of what we're trying to get to here. So those are the various different framework integration options. As to how Arm NN works in a bit more detail as you break it down. So the first thing it does is, so everything is built on top of the Graph Builder API. And fundamentally, that means taking any one of these network representation formats, decomposing it through an importer, and breaking it down and calling into the Graph Builder API that constructs this. So again, TensorFlow, TF-Lite Caffe, you'll have a runtime component that's running on the edge device on current A-class platforms, and it will break down that network architecture and call into the Graph Builder API to produce an internal representation. And that's the same flow that we're using as we deploy on Android NN as well. And so once you've got this Graph Builder API run and you've got the internal graph representation, you then start to look at how you want to interact with this. So we do have an internal file representation, but this is not one of the things that Arm NN generally is trying to achieve. Jem made the joke earlier that F-Write doesn't make a standard, so we basically emit what our internal graph representation is, just for storage and retrieval for various different reasons. But the runtime graph representation is the common format within the Arm NN software stack, and that's used for both consuming your graphs in the first place and representing them, but also running them through the optimizer and running them through the runtime to then decompose them and run them on the device. And then the optimization part of this looks at a few different things. The first thing that happens is it runs through a scheduler to understand which pieces of IP are best for running this workload, and where possible, tuning and fusing operations together. It then runs through the graph optimizer that looks to simplify, and you've got a number of different ways you can schedule networks. You can go either breadth first across each layer of the network architecture, or you can go depth first through various different nodes that are being processed. And so what that tries to do is find the best scheduling pattern statically that will give you the best performance on the target devices that you've selected or that the runtime has selected. And then the third thing that happens are target optimizations. And there are some basic ones there in the optimizer layer. But more often than not, we would expect then that this graph representation is passed into this runtime interface on the right here, through into the plugin device backends. And then each of those can do their own optimizations. So for example, with our MPU, it likes to take the full representation of the graph, so it can change the scheduling order of the graph and keep all of the data resident in local SRAMs to make more efficient use of our NPU. To do that, we need the full graph representation passed through. So we bypass some of the optimizations that happen in the generic optimizer at the top. And we're finding lots of other partners who are looking at integrating their devices have these same kind of needs. So it's constructed to allow people to do that. And the other thing that happens along the way is there's also a memory manager in there that handles the allocation of the major input and output buffers and any intermediate scratch memory that's needed for processing of the graph as a whole, and any memory that's needed for passing operators from, or stages of processing from one device to another if the graph has been broken up to run on multiple devices. The optimizer in a bit more detail, it takes in this initial iNetwork representation of the network architecture that you're running, does validation of the network. You'd be surprised across all of the different machine learning frameworks and the tools that you can use to prepare data, how often mistakes are introduced or redundancies are introduced, like multiple transpose operations that effectively are a no-op. So it tries to work through those and tidy them up. It then modifies for correctness on the target. So reinserts permute layers if you have an operator that only works in a certain orientation of input data. So you may know the NHWC, NCHW formats, so different in-memory representations. It will handle those conversions. Inserts copies and flushes for transitioning between devices, and then tries to modify for performance, so fusing and removing redundant operations to make things more efficient. And then that emits the optimized network object that's an immutable object that then you can then run inference on. And then in terms of how that's actually run in practice, so Arm NN at the moment currently supports 3 backends in the code that we've released. The first is the CPU reference implementation, primarily for testing. So if you're worried about bit exactness with any one of the ML frameworks, you can start to introduce operators with high accuracy there, and then test the other backends that are implemented as well. And we then also expose the CPU accelerated backend and the GPU accelerated backend, both of which are using the compute library. And as Jem was saying earlier, that's the area where we've spent a significant amount of our effort. So the compute library is about 2.5 years now, and has had 10 or 15 engineers working on it for that full length of time, working to really optimize all of the key routines for machine learning processing. And so we've got that targeting Neon. We're using that to track all of the new CPU releases. So as we release new vector capabilities in our CPUs and new versions of the architecture, we'll also expose those as well. And then it also targets the GPU via OpenCL. And so you go through the normal OpenCL driver stack there. The other area, unsurprisingly, that we're working on is this internal backend for our machine learning processor. And so this is a work in progress. So we're revising the device interface at the moment. And as part of this open sourcing and collaborative effort that we're undertaking with Linaro, we're going to start publishing all of that documentation publicly. So if you're interested in working on this device interface, you can come and take a look, or you can talk to me or Andrea about the machine learning special interest group and how you can get involved in all of this. And then, as I mentioned earlier, the deployment for Android NN currently targets the GPU acceleration only. This is because, as I said earlier, we've worked with Google to optimize these routines. So the CPU path goes through the standard TensorFlow Lite route, and then the GPU is accelerated through the Arm NN interface, through the Android HAL. Just to give you an idea of capabilities at the moment, I won't go through all of these in detail, but the major focuses at the moment are convolutional, deconvolutional neural networks, and then also LSTM and other RNNs for audio processing. So all of the examples that Jem was showing, and a lot of the ones that Chris was showing earlier, a majority of those are running. There are obviously more experimental techniques that are coming along, and we'll continue to add to this operator set, but that's where we are at the moment. And then to put that in a bit more concrete terms, if you know neural network architectures at all, so we're looking at these convolutional neural networks that are either doing recognition tasks or doing image segmentation and a number of other ones as well. Okay. And so that's what Arm NN does. What doesn't it do? So we're really focusing Arm NN on the inference. And whilst we do have various stages in here that look at optimization of networks, I think it's important to step back and look at how the entirety of this architecture should work, from the frameworks all the way down. One of the arguments you can reasonably make is that a lot of this processing is not something that should be happening at runtime. It's something that should be happening statically in all of the tools that build up for this problem. So whether that's in the machine learning frameworks at the top during training, where you might want to train and run through quantization and use a retraining flow to increase accuracy, or you might want to look at compilation technology to get a more efficient scheduling of what's being run. You might want to do pruning and other simplifications of the network that increase performance on the target platform. And then a lot of the graph cleaning and optimization that happens in the runtime today is arguably better suited to be put into a tool that is shared by multiple people. So that's one of the areas where we think other tools should be handling this in the longer term, and we need to understand how we decompose these problems so people can work on tools, people can work on inference engines. We have a common interchange between all of those, and more people can be working together on this kind of problem. The other area we haven't looked at, and one of the areas I mentioned, is on the flat file formats and the graph manipulation tools. So one of the things you don't want to get to is a point where you have these formats continuously changing, and you have to keep stepping back and reworking your support for these. So if you're just tracking a machine learning framework, its code base, its new operators, those networks will change over time, and those network representations will change over time, so you have to keep chasing to catch up. So moving to the point where we're working with a common file format for all of this will be useful as well. And then the other area we're not looking at is looking at support in Arm NN, I should say, is training. So that's already supported by the overall machine learning frameworks. That's where it always happens today. One of the areas that will be interesting to look at is integrating these kinds of inference engines more closely into the machine learning frameworks, such that you can use them as part of the feedback cycle when you're training a network. But Arm NN in and of itself isn't going to focus on training. So just then to talk about some obvious next steps and some of the things that we hope you'll start to work with us on. The first are around optimizations. So optimizations to advance the device interface to make interoperation between multiple devices more efficient, working on zero copy semantics and how to handle the graph handoff between multiple devices, adding and optimizing existing operators and adding new operators. So new operators are coming along all the time, new network architectures are coming along, and keeping up with that across the diverse range of markets that people are interested in is difficult. So that's another area that needs some work. And then continuing to improve the representations of networks and intermediate memories such that we get higher efficiency when we're running these networks. The example there being NHWC support to get better bandwidth from main memory. And so that's on the optimization side. And then in terms of new features, so working with offline parsable to some suitable intermediate form. So one of the problems you have is if you try and optimize all the way down to your target, if you don't know what your target is because you're running across multiple different end devices, multiple different phones, for example, then you can't do that. So finding better solutions to getting a more optimal prepared network architecture for running on different devices is going to be important. And then one area that keeps cropping up, but the solution to hasn't been found, is using just classic compiler technology like LLVM to solve this problem rather than building on top of individual operators. And then alongside those options, which look at static scheduling and improving the parsing stages, also looking at how in a heavily loaded dynamic system, you better balance across all of the pieces of IP that are available when sometimes, even though the best device for running a certain network is available in the platform, maybe it's fully loaded with other tasks, so you have to fall back to other devices, and finding ways to handle that as well. And then just to go into a little bit of detail on what the compute library is. So it's a set of optimized low-level functions for the CPU and GPU. Covers both classic computer vision and machine learning functions. The way we're using it in practice is people are using a mixture of the compute library for example, Hog plus SVM and other initial image processing stages, then combined with Arm NN, which calls the compute library for decomposing and managing the neural network architecture itself. And so you can build up more complicated pipelines, including computer vision or signal processing, along with machine learning. And that's also available open source, so you can go to the link there to get access to it. The important thing with the compute library for us is it's where we consolidate all of our effort around supporting current and future architectures. So we're supporting AH32 and 64 for gem and convolution and all of those key functionalities. And as we move to newer architectures on the CPU and GPU, we're also extending support for that as well. It's got support for this OpenCL auto-tuner, and the intent there is that when you're running your network architecture, depending on the input parameters for each of the layers, you can have a very differing outputs in terms of performance that you get on the system. So that's one of the, a nascent static tool for analyzing how best to represent one stage of the network running on the GPU. We will need more tools in that kind of space, particularly for different architectures and different microarchitectures. So that's something we're working on at the moment. And then alongside that, so we've got FP32 support, but we've also got intake quantized acceleration, because for a lot of network architectures, that's proving to be the right route to take for optimizing all of this. And then in terms of where we are with all of this code base, so these are all open source and available now. Up until now, these have been pushed on a quarterly cadence, so every 3 months we make a new release, with the 1808 release being the latest of these. As Jem mentioned this morning, we're going to be moving a lot of this to open source and collaborative development. So all of these code bases will with the exception of SimSys NN today, will be moving over to be managed within the Linaro infrastructure. And we will be developing in the open, having our design work up in the open, so other people can see that and contribute as well. And just finally to say, so as Jem was saying with all of this, it's all about coming together to work on this collaboratively. We're doing what we can, but we recognize even with the 50, 100 engineers that we're spending on the software and optimization in this space, that's still not enough to solve all of the problems that people have, all of the different network architectures, all of the different platforms that people are running with. And so what we're really hoping is people who are experts in neural networks, people who have experience from the past in compilers, people who have worked on, say, heterogeneous scheduling or other problems like that in the past, people who've worked on tooling for performance in other domains, and people who have worked more generally with the machine learning frameworks. All of those people are absolutely critical to making all of this work. And through all of the different companies here, we will have exposure to so many different use cases that people have today, and being able to fold in all of that experience and at least the primitive operators that those different markets need is kind of where we want to get to with all of this. And so you can contribute code directly to Arm NN today. So you can get it from GitHub and start interacting with it and file issues and push features. And as I say, it will be hosted very soon by Linaro on their Gerrit infrastructure, along with bug tracking and mailing lists, so you can start to contribute through the Linaro initiative as well. Okay. Thank you.
Thank you, Rob. Any question?
Thanks for the talk. How well does the OpenCL work with non-Mali GPUs? So are people using like that, or is it specially tuned for Mali, or should it work with other?
So it is standard OpenCL code, so it will work with other GPUs. We've done a lot of microarchitectural optimization to get the best performance on the Mali GPUs. So I think typically what you find is the way we've optimized this, we can get an order of magnitude difference in performance for individual operators on Mali, and I would expect there to be very different characteristics across other GPUs. So work would need to be done to improve the performance there. It's an open question to me as to whether this optimization should be done in the compute library, or people already have their own accelerated primitive libraries for their GPUs or their other pieces of IP that they would prefer to use. One of the many things that we'll be discussing as part of the initiative.
We have time for one more question. Anybody else?
Sorry, a second question.
Sure.
Is there a clear performance difference between the Android stack, where you use the Android one, or where you directly go to the Arm NN?
So on the CPU side, no, because we've been working so closely with Google to make sure that gap doesn't exist. And as we're optimizing, we're pushing those changes through to the CPU backend. Because of the binderized interface, there can be some overheads in going through that full stack down to, say, the GPU or NPU. But we're continuing to work on that to reduce those overheads. At the moment, it's a concern, but it's not a significant concern, so maybe 5% approximately.
Thank you, Rob. Excellent.
Sure.
Thank you.
Thank you.